So this is gonna, okay, so we're starting the recording. Seems like we've settled on the fact that we've already done lecture 4. Just a quick overview. It was mostly circled around electric fields, the formulas for electric fields, given, you know, test charge, the ideals of the superposition principle, yada, yada, yada. Let's not waste time on it. All right, lecture 5, which I think we've agreed is chapter 2. Okay, 22.5 is the electric field. So that is this. I think we said we also went over this last week because we talked about, oh, no, wait, are there 2 Noahs?
No, yeah, I just joined on my phone so that I could like listen.
Oh, okay.
Yeah.
Recording in progress.
Whoa, okay.
Sorry.
You're good. So what we've got is this electric field. So one of the things is, for me, when it comes to, what's the word that I'm looking for? When it comes to learning physics, for me, if you show me this slide, I don't know what you're talking about, right? For me, I kind of need an example. I need an application of this right here. So here's kind of what we're gonna, well, yeah, should we start with lecture 5 and then move on from then? Because then we go into polar molecules. Yeah, we'll do lecture 5.
I'm kind of down for just starting at polar molecules just because
Yeah.
I am trying to go to sleep by midnight and have a bunch of other shit to do. So like
That's valid. All right.
but like if anyone else really wants to do lecture 5, like I'm not gonna sit here and complain.
Did we do lecture 5 in the last video? I don't remember doing lecture 5.
I remember doing it. So I don't know if that means it was like a really long time ago or like what happened, but
okay, that could be true. All right. Anyway, then let's see. We only got up to lecture 3 in the last video. In the last like class review that we did, at least. All right. We'll do 4, 5, and all the other ones another time. But for the sake of this week, then, lecture 6. All right. Polar molecules. This one is a little bit of a hard hitter, heavy hitter compared to other ones. So let's see, polar molecules. I wish I had this already pulled up on the textbook. Huh, okay. So class mostly talked about for that one, the idea of polar molecules, charges within a molecule. I mean, it's pretty straightforward, you know what I mean? In this instance, you have a negatively charged particle, and then you have the 2 positively charged particles, and just the way that the electrons balance out cause it to kind of act in this way. But even though the total charge is 0, they do they respond to electric field? Wait, do they respond to electric field due to charge separation? Do they produce their own electric fields? 2 posed questions. Let's see. Yeah, we really got nothing about I have something about dipoles, but I don't. Okay, great. Here's something. We can do something to find the force that an ion exerts on a water molecule. I feel like that's going to be a pretty good example as for what we do later on. So here's what's kind of important. So you have the dipole moment. I'm going to move this over a little bit here. So the moment P in this instance is equal to the charge times the separation D is a vector directed from negative charge to the positive one. So the dipole movement P is a vector. Wow. Many molecules represent electric dipoles, have non-zero dipole moments. Dipole is supposed to be as small as compared to the scale under consideration. So in this instance, if we were to chart out hydrogen and fluoride, electron poor region. So there's not many electrons on this side, whereas there's a lot of electrons on this side, which makes sense. Hydrogen only has 1 proton in it, so it's only really capable of holding 1 electron. But in this instance, they're all kind of over in this area, meaning that hydrogen would be the positively charged part of the molecule, and the fluorine would be the negatively charged.
So in this scenario, we're assuming that they're full charges, even though they're actually not, like for the math.
Yeah, this is, I guess, like, you know, if you were to just pull it off the periodic table in this instance, so you see here, they are kind of sharing. If I remember, a line was that they have 2 electrons going between them, I think.
Yeah, no, but it's an ionic bond because of the electronegativity difference.
Mm-hmm. Ah, there you go. Remembering the chemistry a little bit better than I am on that one. So then how does this play out? Dipole in an electric field. So this is kind of an example, this one right here, kind of like the capacitor question that we have done in the past. Because what the capacitor question was this was at least, well, in terms of the motion of this particle, if it was going through these 2 capacitors, it would, like, from positive to negative, it kind of just stays in the middle. In this instance, I don't think it is. But so each charge experiences a force F equal to the charge times the electric field. Wait, I can do, oh, okay. I'm going to stick with that, actually. The net force on the dipole is 0 because the forces are of opposite directions. The dipole will not move as a whole in electric field. The forces are applied to different parts of the dipole. Torque may not be 0. Torque is going to be an interesting one to work with, but that is, we are not there yet. So the dipole moment, P, is at an angle theta to the field, causing the dipole to experience a torque. So in this instance, let's see if there's an example for it. In the meantime, I'm going to see if I can find something here that regards to this, maybe. Okay. The right-hand rule, funnily enough, is something that hasn't been, like, thoroughly explained to me. And I just know it's something like, I don't know if it's like a frame of reference thing. It's applied to a lot of things, apparently. So I guess that's why I'm a little rusty on it. So we apply the right-hand rule to find that, I remember it being a thing in Calc 3 with vectors and directions of a 3D graph or something. Apply the right-hand rule to find that both are of the same direction, same sign. Torque equals torque positive plus torque negative equals, so that's going to be the distance divided by 2 times the force plus the distance divided by 2 times the force again. Okay, we'll just kind of keep reading through this. It'll make sense eventually. Magnitude equals, oh my God, torque equals P times electric field sine theta. What's the P again in this instance? That's the
Dipole moment.
The dipole moment. Okay, just making sure. So P is the dipole moment. No, okay. oh, this is rough. Okay. Non-zero torque means the dipole will rotate in the electric field around that point, O, in the middle of the dipole. If the dipole moment is perpendicular to the electric field, sine of theta is equal to 1. Okay, the largest value. So 1 is the largest value, and the torque has its largest, torque has its largest value, as well as if the dipole moment is perpendicular to electric field, the sine of theta is 0. Torque is 0. No angular acceleration is applied. So the dipole tends to align with an electric field. We actually have a few examples of that in the textbook that we can go over as well. When we're talking about dipoles within an electric field. Man, I'm going to be honest. I'm kind of disappointed in this textbook right now. There's nothing talking about, like, nothing explicit. Like, it talks about dipoles. Chapter 23.7, motion of a dipole in an electric field, which is like a subset of what we're learning here. Energy of the dipole in an electric field. U equals the integral of torque dot product, the derivative of theta. Okay.
This is terrible.
That's terrible. I'm going to stick with this one. The negative dipole moment with the dot product of the electric field, which isn't too bad considering those are both vectors. So this is just a dot product question, right? So if at any point a question asks you for the energy of the dipole within an electric field, think of U equals negative PE, basically. Right?
And do we have a example to go with that, or are we just kind of wing it?
I have an example question here that, here's the question if it interests you, but it says the water molecule H2O has a permanent dipole moment of a magnitude, and it gives you the magnitude. The water molecule is located 10 nanometers from a sodium ion, a positive sodium ion, in a saltwater solution. What force does the ion exert on the water molecule? And we could do that one actually if you got, and it relates to the ideal of dipoles. So this is what it is right here. So this is talking about the electric field at 2 points. So let's like try to simplify it a little bit. Let's get the whiteboard out. This one's pretty simple, so it shouldn't take too long, hopefully. So let me ask you guys something. If I flip my laptop like this, can you guys still see my screen?
See your screen or like see your face?
My screen, like the whiteboard
Yeah, we can
stuff.
see your screen.
Okay, that's all that matters. You don't need to see my face. It's okay. Okay, so here's the example that we've got, right? Now this is an equation. The electric field of a dipole is this not going to load? Okay, there we go. Okay. Wow, this is going to be very laggy.
Why don't you just go on a new whiteboard? Would that help?
I don't know. I think it's because I just got a lot going on. My laptop's a little bit on the old side, so. So we have an H2O molecule. I'm gonna write, wow, dipole moment. And I'm gonna write mag for magnitude, right? So that's going to give magnitude 6.2 times 10 to the negative 30. And then you have, so I'll just draw out the figure here. So we have
times 10 to the negative 30, like what's the units for the dipole moment?
Oh, my bad. That is coulombs. This is what it has. It has C and then M.
Coulomb meters, okay.
Yeah. Which is, I guess that makes sense in a way, coulomb meters, because it's I don't know. I feel like it makes sense. Just my intuition tells me so. Na plus.
Well, yeah, because the equation's P equals QD, so that would definitely make sense.
P equals. Very, very true. Very true. So this right here, this is your sodium particle. And then you have this right here, which is R is equal to 10 nanometers. And then you have your water molecule, which is shown like this. And what's going to happen is you're going to have two arrows. So that this arrow is the force of the dipole on the ion. You're butchering that. And then this right here is the force of the ion on the dipole. Right? That's a little arrow pointing on the dipole. Anyway. one thing we want to take into consideration is that Na plus has a charge of positive E, right? And the electric field of the ion aligns the water dipole moment and exerts a net force on it. We could calculate the net force on the dipole as the small difference between the attractive forces on its negative end and the repulsive forces on its positive end. So if we break this down, again, we take into the consideration opposites attract, like charges do the opposite of attracting. Repel, that's the word. Couldn't think of it. Alternatively, we know from Newton's third law that the force F of the dipole on the ion that, wow, that just stopped writing, didn't it? Oh, wow. Okay, never mind. That the force of the dipole on the ion has the same magnitude as the force of the ion on the dipole that we are seeking. We calculated on the on-axis field of the dipole in section 23.2. So this is a bit harping back to something else. An ion of charge Q equals E. So this is charge. Oh, wait a minute. An ion of charge Q equals E. So this is Q equals E. So the charge of this one is E. We'll experience the force of magnitude, and then this is what we get. Force equals the charge times the electric field of the dipole, which is equal to E times the electric field of the, it's not going to do, of the dipole. When it's placed in the field. The dipole's electric field, which we found in equation 23.1. So this is the dipole's electric field equation.
Okay.
Goes like this. It goes, the electric field of the dipole is equal to 1/4 pi times epsilon naught. And then you have 2 times the whatever the P was again, I forgot the term for it, not squared, cubed.
Wait, what's on the top again?
That's 2P. Sorry, that's a little hard to read.
And what's, so P is our dipole moment.
Dipole moment, yes.
Okay.
I'm gonna write that down. So the dipole moment is pretty, well, that's kind of given, isn't it? It's pretty straightforward. 6.2 times 10 to the negative 30. So
wait,
what
was
this
that
says,
given in our equation?
Yes, that was given initially.
Oh, okay.
This says the force on the ion at a distance of r that, hold on, let me double check this.
Oh, yeah, that was given.
So this is kind of what they have written. So there's this equation right here. And then what this says is, now we're gonna do the force. Oh, I see what they're doing. They're kind of, I think they're kind of doing this like the Coulomb's law at some point as well, maybe, I think. Force on the ion at distance. I guess you have to consider that distance is not represented in this. So then if we look at force of the dipole on ion is equal to E times the electric field of the dipole. So all it really is It's just one difference. I guess it depends on how you want to write it, but it goes 1 over 4 pi times epsilon naught times 2. I'm going to write it a little bit differently because I need to separate it in my brain, times E. Does that make sense there? The way
Okay,
they
so we're
have
just
it.
plugging in for the electric field.
Yep, basically.
And we can use that 1 over 4 pi E naught, or epsilon naught, my bad. That's just K, right?
That is just K, yeah.
Okay.
I guess, yeah, let's actually simplify this all the way, yeah, because we could do K times 2 dipole moment over R cubed times E. That's pretty straightforward, actually. Okay, not too terrible. And so the charge that we get when we plug everything in, we get 1.8 times 10 to the negative 14 newtons. That's what we get. Now, while 1.8 times 10 to the negative 14 may seem like a very small force, it is 10 to the 11th power times larger than the size of Earth's gravitational force on these atomic particles. Forces such as these cause water molecules to cluster around any ions that are in solution. This clustering plays an important role in the microscopic physics of solutions studied in chemistry and biochemistry. That's really interesting, I guess. Okay. That was pretty straightforward.
Yeah, wasn't bad.
Yeah, I guess straightforward, I guess, is the nice way of putting it. All right, the dipole so you guys can see that I'm on the PowerPoint now?
Yeah.
Okay, so now we're talking about the dipole electric field at 2 points. I'm going to be honest, I don't really see this as being all that different from finding the, like, this is just the same kind of break down the vectors, see what the electric field is of this dipole at that position, right?
Yeah, it
Just
doesn't seem like
right here.
different from what we've been doing.
Yeah, with the same superposition principle and everything, like that's all this is, like, and that's what we're seeing. So the positive and the negative are exerting their own electric fields and they're interacting at different points, kind of like this example we're seeing, and they have different direction vectors and everything. So that's how I see it. Anyway, electric field of the dipole. If the scale is much larger than the dipole size, an approximation can work. So we have all these fun little equations. Close view, very complex, hard to describe by a single formula is what we have on the PowerPoint. So I guess we have 2 different equations here which describe the electric fields of the dipole in terms of X and Y. Yeah. So this field is 0 in terms of
just what we had, right? Like that's like what we just used for our equation.
Yeah, I guess this is if you were to kind of break down the, maybe, I don't know if saying the vectors is the right, chapter 24. Okay, wait, okay, now I know where we are. That's good to see. Yeah, this shouldn't be too crazy. So chapter 24 in the textbook that we have is called Gauss's law, which, oh yeah, flux, the concepts of electric flux. Okay. So first, this talks about symmetry, actually. So Gauss's law is a general statement about the nature of electric field, symmetry. So what is electric flux? This is actually, I had no idea what he would refer to, but the amount of electric field passing through a surface is called the electric flux. The electric flux is analogous to the amount of air or water flowing through a loop. You will learn to calculate the flux through open and closed surfaces. So that's what it is. When you think
you said amount of electric field?
Yep. The amount of electric field passing through a surface is called the electric flux.
Oh, okay.
And then it compares it to the amount of air or water flowing through a loop. And that's what we kind of see here. you know, in this image, we have a rectangle and we have electric field vectors passing through a certain area. There's a few questions about symmetry, but we are not going to focus on that one way too much. We just want to get to flux. Flux is a non-uniform field through a curved surface is defined. The flux of a non-uniform field through a curved surface is described by a special kind of integral called the surface integral. Okay, well, let's look at the PowerPoint here first. The dot product of two vectors is a scalar. Theta is the angle between the vectors. That one's pretty straightforward. Electric flux is defined with the symbol. I don't know what that one is, but there you go. Here, A is a vector normal to the surface, magnitude A, and direction normal to the surface outwards in a closed surface. You can think of flux through some surfaces as a measure of the number of field lines which pass through that surface. Flux depends on the strength of the electric field on the surface area and on the relative orientation of the field and surface. So the flux is the electric field. The flux is the electric field dot product with the area. Now, here's one thing, the normal to surface magnitude A, okay. What? Electric flux is a scalar product of two vectors, electric field and the area, which is also the electric field times the area times the cosine theta. Flux
How are they
depends on-
representing area as a line? That doesn't make any sense.
I'm going to assume this is,
I think in this example specifically, they're only showing you the side view, but if you go
Yeah.
up, it's a square.
yeah, it's all about the dimensions. In this
Yeah.
case, I think it would be dimensions.
Yeah.
The number of field lines through the tilted surface. Okay, so this is in a two-dimensional sense, this right here. Pretty straightforward. Do I have an example question here? I would love to do an example question. Flux through a curve.
Do you want to quickly run me through what we're doing real quick? I just got here.
Oh, so we are on chapter 24. We are talking about electric flux through a surface.
Okay.
Yeah, which I guess if you wanted to be, that's lecture 6. Oh dear.
I found a textbook very, very useful.
That's what I got right here.
Yeah.
Textbook.
Absolutely. Showing up to class has just kind of been a refresher for what I've been reading.
That's very true. That's kind of what I've been trying to accomplish this semester, is like going to class as a refresher while I'm able to read and study everything outside of class. I was a little lazy this weekend though, I will say. But anyway, let's keep killing it. Yeah, let's do it. So this is, as far as I can tell, when we're talking about a two-dimensional system. But what if the surface is curved or the field varies in position? Look at that. Who could have seen this coming? Who could have seen this coming? So our equation changes. So we divide the surface into small regions with the area dA. This is almost reminding me of when I first started learning about integrals in Calc 1. I think it was integrals, derivatives, all that stuff. I remember my teacher going up and drawing the little rectangles under the graph, and she said, make them infinitely small. I was like, amazing. So the flux through the D area is, well, let's break it down here. Basically, it's equal to the electric field with the dot product of the derivative of the area. So to obtain the total flux, we integrate over the surface area, over the surface A area, not the surface area specifically, which makes sense, I guess.
right.
So here's what we've got. The surface area of a sphere's radius, da, da, da. Oh, this is talking about the sphere specifically. Maybe I should read through this whole chapter when I get the time. In the case of a closed surface for an external field, no source of field inside the surface. The number of entering lines is equal to the number of outgoing lines minus the total flux, 0. So I guess if we ever get a test question that says, hey, what is the electric flux of a closed surface where there's no source of field inside of the surface? I'm guessing it would just be 0.
Yeah, that would be a great test question.
That would be a great test question. Because I know that I, for example, would go through the headache of doing the math and then have a panic attack when my answer is 0, you know, so that is something I would do. So easy to prove for uniform electric field and cubic closed surfaces. The electric charge is a source of electric field. There is no charge inside of a closed surface. Flux through that surface equals 0. So I guess when we think about flux, we want to think about it, from what I'm seeing here, it has the condition that the charge is coming from inside of the object. When we were talking about it in a two-dimensional sense, it looks like it talked about the electric fields just passing through a surface, but now we're getting more into, hey, if it's not coming from inside of the surface, it doesn't really count.
Yeah.
That's my guess on this one, you know.
No, I feel like that's, yeah, because like when I was reading it, I was like, is the charge not passing through? And that's where I was getting confused.
Yeah, that's what I'm with you on there. So this is the electric flux through a closed surface. So to calculate the electric flux through a closed surface, such as a box, we've already learned how to calculate the electric flux through a flat and curved surfaces. So a closed surface is nothing more than a surface that happens to be closed. Think about that. That's crazy. However, this is however, the mathematical notation for the surface integral over a closed surface differs slightly from what we've been using. It is customary to use a little circle on the integral sign to indicate that the surface integral is to be performed over a closed surface. With this notation, the electric flux through a closed surface is, imagine something like this right here, that E equals, or E times dA. But the only difference is, well, there's little vector lines over the E and the A, and there's a circle over the integral.
Oh.
So with this one right here, we're talking about negative electric field times L squared. So that's for face 1, which would be, the one on the back. Okay, for phase 2, and for the other sides, it's 0 for some reason.
Well, I think it's just because if you look at like the E with the like arrows.
Yes, and the electric charge is not passing from inside of the box. This is just a proof of what we just read above, I think.
Yeah.
Okay. In a sense, it's almost like it just all kind of cancels. It seems like more complicated case of closed surface results in the same. For the external field, no source of field inside the surface. The number of incoming lines equals the number of outgoing lines. And I guess that just makes sense, because when you think about it, if the charge is coming from inside of the object, then it's like, hey, the number of outgoing lines is not the same as the number of ingoing lines. So this says the vector, let me move this, the vector calculus fundamental theorems are used to prove, not in this course, they're gatekeeping information from us. How bad. All right. Okay, let me see if we have any example questions we can do from the textbook.
Okay.
Thankfully, it looks like we do have a few that we can use. Oh, we do have quite a few that we can use. Ooh, okay, this is a good chapter to be on. Okay. Lecture 7. There's 20 slides in this one. Oh my God. Okay. Quick review. In the case of the closed surface, there's no field inside the surface. The total flux is 0. A charge, put me back on the bottom. A charge source of electric field is inside of a closed surface, meaning in this instance that there are no incoming lines and that all lines are outgoing, so that the flux does have a value. Change the shape or size of the closed surface. Oh, so no matter the shape, the flux is the same because it's the same amount of electric field vectors that are exiting this object. Flux doesn't depend on shape and size of the closed surface. What does it depend on? Let's see. Flux of electric field is due to a positive point charge Q through a sphere of radius R centered at the charge. Direction of the field everywhere at the surface is the same as the direction of vector A. The magnitude of the electric field everywhere on the surface of the sphere. The magnitude of the electric field everywhere on the surface of the sphere is E equals K times the charge over R squared. R squared, I guess, would just be kind of like the diameter in this case.
Well, like the radius, right?
Well, yeah, but I guess that's true. R is the radius, but I guess when you square it, I thought of it acting like a. It's been a long day. You're right. R is the radius. Okay.
No, I may not know what a surface integral is, but I know that R is radius. So I'm just
We're at a good starting place. So we have the flux of the electric field is equal to 4 pi k times the charge, which is also equal to the charge over epsilon naught. I think this is when I also asked him what the exact value of epsilon naught is. Yeah, and then it goes right to it. The value of epsilon naught is 8.85 times 10 to the negative 12 coulomb squared. Electric flux through any closed surface always equals to the enclosed charge divided by epsilon naught. That is so straightforward. Just get the charge of the thing and divide it by epsilon naught. That's all it is. And then bada bing, bada bang. And then look, we're moving on to multiple charges. That's all we're doing. So let's do an example question before we move on to multiple charges, because I have an example question for this one that we can do, right? Okay. So here's what we're going to say. We're going to keep it on blue. So okay. I'm gonna, let me read this. So the electric field, there's an electric field inside of a closed cylinder, right? And here's how it's gonna look. So this is like you're looking at top down. Wow, that's a wacky line. There we go. X and Y. Now this is going radially out from the center like this, like that, in just about every direction. At every 45 degrees, there is a vector. Shit, I committed to drawing this, didn't I? Okay, let's see. Like that. Okay. Okay, not bad, not bad. Boom. All righty. So then the vectors are coming out like that. Do you see? Okay. It is symmetrical around the z-axis. It is a closed Gaussian surface for which we need to calculate the electric flux. We can place a cylinder anywhere along the z-axis because the electric field extends forever in that direction. To calculate the flux, we divide the closed cylinder into 3 different surfaces: the top, the bottom, and the cylindrical wall. The electric field the electric field is tangent to the surface at every point on the top and bottom surfaces. Hence, according to step 1 in the tactics box 24.1, which is earlier, the flux of these 2 surfaces is 0. The top circle right here and the bottom circle, flux is 0. Because like, you just got to think of it like a really thin thing, you know what I mean? So nothing's technically passing through. For the cylindrical wall, the electric field is perpendicular to the surface at every point and has a constant magnitude. E equals E naught times R squared over R squared naught at every point of the surface. Thus, from step 2 in the tactics, this is referring to something earlier, we're going to work with the flux of the wall is equal to the electric field. Sorry, I got distracted for a bit. The electric field of the area times the area of the wall. This is really okay. Oh dear. So this is all kind of like wasted writing here, what I'm gonna do, but maybe it'll help you guys out a little more than it helps me, but I think it just explains a little bit more as for what we've got. Because what this says is that the flux at E is equal to the overall integral of the electric field vector with the dot product of that. And this is essentially equal to the flux of the top plus the flux of the bottom. I'm just going to write bot for bottom. And then it's going to be plus the flux of the wall. Can anyone give me a guess what this equation is going to look like when we plug in, not numbers specifically, but just what it might look like? Excellent suggestions. So this is going to be
Okay,
0
okay, give me a
plus
second
0.
to think. Jesus. God, it's tough out here, okay?
That's fair. I'm the one with the book, so I do get that advantage. Yeah.
Wait, hold on. No, you can keep going. I just have the textbook as well. I just realized that.
Oh, there you go. Okay, yeah. So this one, just kind of what we said earlier, 0 plus 0 for the top and bottom, because those aren't going to have any flux. And then we're going to have the flux of the wall, which is E times A of the wall. So we've evaluated the surface integral using the 2 steps. What are the 2 steps in this box it keeps talking about? It's not that helpful. We've evaluated the surface integral using the 2 steps in the tactics box there, and there was nothing to it. To finish, all we need to recall is that the surface area of a cylindrical wall is the circumference times the height. That's all it is. So this is a little bit of like Gosh, when did I take geometry? Middle school? So cylinder wall is equal to circum times, I'm going to say h for height. We can all agree on that. Or, and then this goes to be 2 pi times the radius times the length. Length is the vertical component in this instance. So the equation that we get, let's see, did we write it down earlier? Yes, we did. So this right here is what we're going to be using. Except in this instance, we're also multiplying that by the area of the the area of the cylindrical wall is what we're doing. So the way that's going to look, the equation is going to look a little bit like this. So the total flux, in this instance, that's an E, should be an E, okay, is equal to, this is our first equation that I was talking about, the electric field naught times the radius squared over, or over the distance. I guess this question really doesn't give us a numerical answer, but it is a symbolic one. Because then this goes to pi RL.
Okay, so here's what I don't understand now. I thought that this was a closed surface.
This is a closed surface.
And then isn't the flux 0?
Oh, no. I was, that's why earlier I said the electric field is coming from inside of the cylinder here.
Oh, okay,
Yeah.
okay.
The electric field, yeah, it's inside the cylinder along the z-axis is what we're doing. You know, so that is our best, that's what we've got. Alrighty, that was a little messy. I need one with like a number answer, man. That's what I need. Okay, let's keep going. Electric flux of multiple charges. This is funny because it's right out of the textbook. So one of the things is that we need to take into consideration the superposition principle. So the electric field is the addition of all the electric fields and the effects that they have on each other. So in this instance, you would do the, does he have the equations here? He doesn't have the equations. So defining the charge interior to be the sum of all charges inside the surface, we find that these flux is equal to the inside charge divided by epsilon naught. So, man, I got eaten by bugs today. That's crazy. All right.
Oh, were you out for Memorial Day?
Yeah, I was just kind of like, just being outside to like get to my car. Like it's just really mosquito-y today. But yeah, I've been out and about today. From the principle of superposition, the fields are, thus the flux is equal to the integral of electric field of 1 dot product dA plus the electric field of, plus the integral of electric field 2 dot product dA, et cetera, et cetera. In total, as total charge enclosed within the surface, with this definition, we can write our result for the net electric flux in a very neat and compact fashion. For any closed surfaces, enclosing a total charge of Q internal, of internal charge, the net electric flux through the surface can be written like this. Integral electric field times, that's a times. Oh, come on. What? There you go. dA, which is equal to the charge inside epsilon naught. This result for the electric flux is known as Gauss's law. Gauss's law doesn't say anything new or anything that we didn't already know from Coulomb's law. Or I guess we should go along with his presentation though. The integral of E times da, da, da. Oh, that's actually just what we were talking about. Flux of the electric fields in both surfaces is the same. What if we increase the radii of the surfaces without changing the amount of charge inside? The flux does not change, which is kind of crazy to think about in my opinion, because like honestly, like the charges are kind of not changing direction, but in regards to the surface, it kind of throws me off. Flux will not change. Electric field decreases, surface's area increases. If the total charge inside of the flux, oh dear, inside is the same, flux is also the same. Interesting. Alrighty. Calculate the electric field produced by a point charge using Gauss's law. We choose for the Gaussian surface, a sphere of radius r centered on the charge q. Then the electric field E has this, okay, actually wait, we have an example question that we can do here. In chapter 23, outside of a sphere charge, does he have the work for this one?
Is this like an actual, like, I don't see any numbers. Like, are we?
I think this is more like proof wise.
We've got a question. What's spherical? Wait, wouldn't it be the same?
Wait, what are you talking about?
The question, the spherical Gaussian.
Has the larger electric flux. I want to go with B on this one.
Oh, wait, why?
It only depends on the enclosed charge. Okay, let's see what we got. Let me see if this question is one we can do. The trend of the sphere. I'm bringing my textbook to the recitation tomorrow as well. So we know.
Oh, wait, for recitation, do we like, I don't even know how that works. I never went to my physics 1 recitation. Do we work on it together? Like the worksheets?
Usually, in my experience in my physics 1 class, it was kind of frustrating because the way recitation worked was the first week we had recitation, it was like a review session, which was all well and good. And then the second review session, they said, oh, we have a quiz this one. And then after this quiz, you guys can go home and you're good. It's okay. We did the quiz, we went home. And then the next week it was, hey, let's review the quiz. And then you can go, oh, okay, we review the quiz. It takes a whole recitation time. And then they're like, oh, by the way, quizzes are every 2 weeks. So you have a quiz next week. So it was very frustrating because I never got it as a review class. It was more of a quiz class.
I see.
Quiz and review, yeah. So it wasn't that fun. Outside a sphere of charge, So I do have the example question for this one. This is really nasty to look at. I'm going to be honest, but here's the thing. It's sorry, I lost my train of thought for a second. The way they do it in the book is a little bit better, I think. So let's, but here's the thing, you get the same result here. This right here, the E of R is equal to 1/4 pi epsilon naught times Q over R squared. In the book, the only difference is instead of E of R, it says, hey, E, the electric field, sub, and it says outside. That's all it is. It's the same kind of proof. And in this instance, R hat is a radial unit vector. Take that for what you will.
Right.
To calculate the flux, notice that the electric field is everywhere perpendicular to the spherical surface. All right, let's move on here. Let's see. So in this instance, the spherical Gaussian surface of the equal radius R surrounding two spheres of equal charge Q. Which Gaussian surface has the larger electric field? Now keep in mind that the kind of flux questions and everything, though in terms of electric fields, it depends on the internal charge. So I'm going to go with they have the same electric field on this one.
And you're saying that because the charge is the same, right?
Mm-hmm.
Okay.
That's what I'm thinking. Let's see. Yo, awesome. I should get like a surface tablet or something because like writing with my finger, I feel like I should be writing down these equations, like cruising through it, and it bothers me that I'm just like reading.
Wait, you're writing with your finger?
Yeah, I'm writing with my finger on my laptop screen.
Oh my gosh.
Yeah, that's why it looks so bad.
Oh my gosh.
Yeah,
funny.
so let's see how to solve it directly by applying Coulomb's law. So this is kind of a similar concept. Oh wait, what is this? Taking this as a volume integral would be hard. Gauss's law is easy. Good to know. It's clear that the net electric field at this point will be horizontal, but the magnitude from each bit is different. And it's completely not obvious that the magnitude of the electric field just depends on the distance from the sphere's center to the observation point. Wow, that's crazy. The electric field of a charged thin sphere. Oh my God. What in the world is this? What are we doing? Okay.
Wait, okay,
this
hold
isn't
on.
even in the textbook. It's not even.
If it's not in the textbook, I vote we just skip it.
Okay. It's just wait. What's this equation we were looking at earlier? 1/4 pi epsilon naught times Q over R squared. 4 pi epsilon naught Q over R squared. 4 pi epsilon naught Q over R squared. It's the same function. Just think of this function. Okay. It's the same function right here. Again, E is the same as for a point charge inside and all this stuff. So problem. Sphere of charge Q. The electric field in terms of R at a point inside the sphere. So now instead of talking about the electric field outside of the sphere, like the equation we were looking at earlier, we have a different one. Instead, we're talking about the electric charge inside of it. All that changes is it's the charge divided by the 4 pi epsilon naught times the radius cubed. The radius is the radius of the sphere, but then you have R, which is the distance to the inner sphere. Hold on. Do I have anything? Yes. So it looks like the textbook kind of Okay. Wait, is this the same? Okay. We can do this one.
Okay.
We got this one. This one's easy. This is a cakewalk. Watch this. Here you go. Okay, so we have a bunch of positives inside this thing, right?
Wait, is this the same question on the lecture slides, or are we doing it like an example?
This is kind of like the lecture slides. Let me get the lecture slides. I was basically going to do the proof that is shown here in the way that the textbook does it.
Okay.
I'm going to be honest, I find that the textbook actually kind of explains the proofs a little bit better, I think.
All right.
Or maybe not. Hold on, Coulomb's, Gauss's laws, QV inside. Q inside equals rho VR.
So it kind of
Okay.
looks like the only difference is that they're coming up with an equation for the enclosed charge, right? Like that. You would agree with that?
Yeah. So, okay, so it looks like the differentiation between the radius and the little r is that the little r is the Gaussian surface inside the sphere of charge. And then r is the whole circle.
Okay, so
we kind of
big
see in
R
this
is our
picture.
big radius and little r is our little radius.
Yeah, exactly. And I think, and you know what's frustrating? They have it flipped in this picture. Right here, the big R should be the big line and the little r should be on the little line. So this is not like the PowerPoint is helping you all that much. And this one's even more complicated because, yeah, they have it flipped here too. Yeah, okay.
Oh man.
This circle right here is right in terms of how it's shown in the textbook and the fact that it corresponds with the equation that we're working with. That is bullshit. That is such bullshit. So the field inside and the field outside of a sphere of a charge match at the boundary of the sphere. At this point, r, little r, is equal to big R, where both give that nasty equation of the electric field is equal to Q over 4 pi epsilon over, where do we have it? This equation right here, where both give this charge, meaning the charge of small r and big R are both giving that charge. In other words, the field strength is continuous as we cross the boundary of the sphere. What does that mean? I'm just going to keep reading. These results are shown graphically. So this is talking about field strength. And according to this, I don't know what boundary it's referring to in this one. Because in the picture, in the diagram that they just have a regular circle, just one circle. And it has the radius R, big R, and the radius, like the outer sphere, corresponds with big R in this chart right there.
Okay.
Which makes sense. But I guess that's the outer sphere of the overall charge, the big circle, and the little circles inside of that. That's what I'm going to go with. That's what I'm assuming. but it looks like it says E of R is proportional to 1 over R squared for all values where the little r is bigger than R. Okay. I think this has it flipped again. I have a weird feeling that it does because here's what I'm, man, could I have them flipped? That's what I'm worried about. Because here's what I'm thinking.
I mean, what kind of question would be even be asked about this?
Yeah, the drawing they have is like this. You have your arrow, and then this arrow is big R. I don't know what kind of question they would ask about this actually. Let's move on. Yeah, that's a good point. Let's just clear all the drawings and move on. Let's not lose too much sleep on it. Okay, now we have the cylinder. All right. Field at a, okay, actually let's move on to the next PowerPoint just because we don't review it. Okay. Field at a distance from a line of charge. So in this instance, all you're really doing is, looks like the biggest difference here is that you're now introducing lambda again. So the electric field has an axial cylindrical symmetry. Select a cylindrical Gaussian surface. The cylinder has a radius of r and a length of L. Okay. Use a constant magnitude and perpendicular to the surface at every point on the curved part of the surface. E is constant in magnitude and perpendicular to the surface at every point. So the electric result is the same as we got by integrating Coulomb's equation, but it is much easy to get it by applying it is much easy. I love that. That's by applying Gauss's law. So it looks like the equation that we're going to run with is this one on the bottom right-hand corner. And it looks like that's what the textbook also runs with, where the electric field of the wire is equal to lambda divided by 2 pi epsilon naught r. And I think it's because, does that also incorporate the surface area of the cylinder? Probably.
I don't know.
Okay. We are like just plowing through this, you know, we are just kicking ass and taking names on this one. Yeah, exactly.
Are we gonna do another Zoom some other time this week?
Yeah, I'm definitely planning on it. I'm definitely gonna need the review.
Like what day are we thinking? Because I do have a calc exam on Thursday.
Ooh, you know, that's a good point because I have
I could do Thursday, but like Wednesday would not be good.
I'm down to do Thursday because I do also have a CS2 exam on the 6th and I need to do good on it. Okay. Should we just leave this for that day then? It is a little late and I need to get up early tomorrow.
So do I. God.
Right. Sounds good then.
I'll probably just review it on my own a little bit.
Definitely. If you want to rewatch this video at like half speed, I highly recommend it. But all right, we'll finish the review and everything later this week. I also need to just kind of like freshen up on this stuff. That way, like in this review session, we can actually be like maybe a little more productive than just reading the PowerPoint. I think. I don't know.
I mean, whatever you want to do, man. Like,
all right. Well,
you're the boss.
Well, we'll get her done. You know. Well, we gotta. I don't know. We'll see. But anyway, I'm going to sign off now. I'm going to get some food before I go to bed and everything. So I will catch you guys tomorrow in class, maybe. If anyone in here had a Monday recitation, which was supposed to be today, I have mine at, let me check. I forgot what time. 1 o'clock tomorrow. And I will be in there the whole time reviewing the recitation and just about everything. So if you want to hang out, I say come join us. So yeah, I'm gonna stop sharing my screen here. Alrighty, so I guess you guys get out of here. It was a fun study session. I'll see you on the next one, all right?
Yep. See ya.
Alrighty, take care, Noah.